Okay. Well, I think I hit a button, so let's do some stuff. I really like the stuff I was doing Monday, which was I introduced you to these vector value functions, and then it didn't take long to do some derivatives and call those derivatives velocity and acceleration vectors and drew them all together. I mean, that's a good lecture. I mean, that makes sense. If I ease my way through this homework, it's not as fun. The homework starts in 12.1 with a lot of sketching, and then I guess you're plotting points. Although, perhaps I could tell you this. I don't know if you knew this. They do ask these questions about domain. I'm not too concerned about that. What can you plug in for t? Evaluate these. So some of them are plugging things in. But if I saw this one, and they say to sketch this, 2 cosine t sine t. We talked about this. Oh, by the way, the book always, of course, uses the I and J and K notation quite a bit, but I always kind of use this vector notation. But if I wanted to sketch this, I'm good at this. I wonder what you might remember from Monday. Any ideas popping into your head?
It's a circle.
Good. I mean, you're wrong, but that's the idea. We did discuss circles. Circles are when you have that cosine and sine, but what really makes it a circle is when these coefficients match, because then it's a circle of a certain radius, 1 or 2 or 3. But when they don't match, then it's kind of like a circle with 2 radiuses, which is an ellipse. Yeah, that's bad language, maybe. And in the x direction, it goes out 2 and back 2, because of that radius of 2, so to speak. But in the y direction, it's 1. It's kind of got a radius of 1. So this actually is an ellipse. Do you remember the orientation of it? In other words, it either goes clockwise or counterclockwise or clockwise.
Counterclockwise.
What'd you say?
Counterclockwise?
One or the other. When we wrote cosine first, that's kind of the typical unit circle movement, which is counterclockwise, yes. Yeah, right. So it is counterclockwise. We could even discuss the period, so the 2 and the 1 are affecting the radius, so to speak, which makes it an ellipse. The period was the time it takes to do 1 revolution. And the period can be calculated using this coefficient, which is actually just the coefficient of 1. And when it's a coefficient of 1 on t there, the period is, do you know?
Pi over 2.
No.
2 pi or it's just 2 pi?
2 pi, yeah. 2 pi. It's 2 pi divided by that number. When that number's a 1, it's 2 pi. Right. So, this is a classic, nice elliptical motion. It starts here at t equals 0, it goes around, it comes back, it ends here at t equals 2 pi. It doesn't really end. It goes forever, it just keeps going round and round and round. It's kind of fun to think of t as time, like it's here at this time, then it's here at these other times. It is kind of convenient to think like that, but we're in the abstract math world. T is just a parameter, it isn't necessarily time. I mean, then if you do call it, then you're kind of in a physics problem where t is time and x is feet and y is feet, and but cool. What I was going to say is, you might think that because t is time, that it has to be a positive amount of time or something, but no, okay, t is just a parameter. T could be negative. For negative values of t, you're going, well, I say this, t equals 0 is here, you start here, but if t is a -1, you're back here somewhere. T is a -2 or negative, I mean, so the domain of this is, you know, t could be any real number, you know, all real numbers from -infinity to infinity. But when it's this circular motion, we tend to focus on one lap, you know, this is one lap around. Okay, so like I said, if I'm sort of sticking in 12.1, then all I'm doing is sketching and thinking about it. I was tempted to go, let's do some derivatives and draw some velocity and acceleration vectors. I do like to do that, but that's kind of my question, which sort of merges 12.1, 12.2, and 12.3 together. But look for those questions on tests and quizzes where I ask for velocity and acceleration vectors, and I ask you to sketch them at a certain point, yada yada. We practiced that Monday. Oh, I wanted to tell you how this works on your calculator. Without turning on my calculator, I just want to point out in your calculator, you know, your TI-83 or your 84, if you have a Casio or something, I'm not sure exactly how that one works, but what you can do is you can graph parametric equations, but you have to go to mode, and you have to go to where it says function. You've always probably been in function mode, but you can get yourself in parametric mode. And once you're in parametric mode, when you type y equals, what you see in y equals is you see x1 of t and x2 of, no you don't. You see x1 of t and y1 of t. And you can type in these parametric equations. Did you know that? Yeah, well, that's good to know, man. That is real good to know. Did you see that under mode? Go down to parametric mode. Can you find that? Hit mode and then go down to function and move over to parametric mode. Yeah. And now when you hit y equals, instead of a function of x, and you could actually type this in. Well, you could type in 2 cos t, and you could type in sine t, and you can use your graphing calculator. When you try that a second, and then do another thing for me. Let's see, since we're dealing with trig, we probably ought to also be in radian mode, I think, instead of degree mode. That's kind of a good idea when you're dealing with trig. And then when you mess around with your window, you can mess around, and there's a t min and a t max, and a t step. Am I right, you guys? Are you seeing that?
Yeah.
Now, so you know already. We've analyzed this already. You know that a good t min and t max might be 0 to 2 pi, right? And then you see it. Then you see one lap of the ellipse, and you don't need to see more than one lap. But check this out. This t step. You know, watch what happens if you do too big of a t step. You know, by the way, 0 to 2 pi in numerical terms, that's kind of like 0 to 6, right? Would you agree with that? That's roughly a 6, 6.28. So if you do a t-step of like 1, then it's only going to plot 6 points. And you can try that and see how bad it kind of sucks. What your calculator does is it plots 6 points evenly spaced around here, and it connects those dots, and your ellipse kind of looks like this. Am I right? Did you try it? What am I saying? I'm saying try typing this in.
Oh, yeah.
And I'm saying try a t-step of 1, and I'm right, aren't I? Let me just see.
Yeah, I think so.
Oh yeah, do another thing. Hit zoom, and go to zoom decimal. It's just a kind of a zoomed in window. Yeah, it's just a... But anyway, that's too blocky, right? So I'm explaining your calculator to you a little bit, but I'm saying that it's plotting too few points between 0 and 2 pi. So a common t-step would a 0.13. I've seen this. I think and I don't know, see, by a default setting that was 0.13 something, 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 so I've kind of memorized that. Or a 0.1 would be good. And anyway, then it plots a hell of a lot more points and you get the curve, you get more of a curve.
Mm-hmm.
But I'm just talking about setting the T window. Of course, you can also set your X min and max. You can set your Y min and max. That comes below there to get a good looking window, to see a good looking graph. You know, what else did I think I thought? Oh, remember how when we graph these then, we want to show orientation. So I needed those little arrows to tell me the direction of increasing T, counterclockwise or clockwise. And you guys figured that out. But now that you know how to use your calculator will sort of show it. In other words, when you hit enter and graph it, if you watch it while it's being graphed, it will graph it in the proper orientation. You know, I mean, it'll graph it in the direction of increasing T, which is what the orientation is. So you can kind of watch it, and then you'll see, oh, okay, it's going counterclockwise or clockwise. Once it's already graphed, it doesn't do that again. You almost got to clear the graph and do it again to watch it. You got to just watch it that first time. Well, so this is cool, man, and your calculator will help a lot for graphing some of these two-dimensional things. Listen, though, your calculator won't do three-dimensional space curves, so then it's up to us to know some stuff. I don't ask you to draw crazy three-dimensional space curves. Do you remember which kind of three-dimensional space curves I did ask for?
Yeah, helix.
Thank you. They're helixes. Yeah. Yes. I mean, here's one. Here's 21. I'm looking at your book. I'm in 12.1. Trying to look at some of this beginning homework. 21 is a vector value function. Again, they write it in terms of I, J, and K, and I kind of take it out of there, and I'm going to write T squared, e to the 0.75 T. T squared, e to the 0.75 T. Well, anyway, that's not a helix. If you remember, the helix had to have sine and cosine. It had to have that circular motion, and then a third dimension that wasn't circular. I mean, so this is not a helix. It's some three-dimensional space curve, though, and I really don't have too many good techniques for you here. I think I should plot points. Let me try a few things. I'm going to plot points. If t equals 0, so what am I doing? I'm making a chart. I'm plotting some points. T equals 0, and then what's r of t? R of t is a vector. If t is 0, what do you get? 0, 0, and e to the 0 is 1. Now keep in mind, this is 3 dimensions. This is going to be a messy graph if I start drawing this. What I have here is a position vector. And the position vector is 0, 0, 1, which starts at the origin, goes, let's see, what is 0, 0, 1? 0 in the x, 0 in the y, 1 in the z. So it goes up 1. Now, again, keep in mind, it's a position vector that goes 0, 0, 1. So here it is. But what I really am concerned about is where the vector ends up. It ends up at the point 0, 0, 1. And I don't really need to see that the vector took me there. You know what I mean? This almost becomes, this plotting points is kind of funny. I am almost really equating vectors with points, aren't I? Because I'm only concerned with where they end up. Again, I don't really like to say vectors are points, but they almost are in this world. Yeah, what do I do? Plot more points. When t is 1, I get 1, 1, e to the 0.75. Well, I'm not exactly sure what that is. Maybe you can pick up a calculator and help me. Maybe it's 2 point something or...
Oh, yeah, 2.12.
2.12. Okay, well anyway, 1, 1, 2.12. 1, 1, and then up 2.12. Boy, oh boy, there it is. But it's out 1, it's over 1, and it's up 2.12. I mean, it's out and in front and away from that point. It looks like it's right next to that point. You know, that's the problem with drawing 3D on a 2D blackboard. Let me try another point. I guess if I do 2, what's 2? 2, 4, 2, 4, and then e to the 1.5, if I plug in a 2.
4.48.
Thank you, about a 4.5 roughly, she says. So that means I would come out 2, over 4, and up 4.5. Again, it looks like it's net, but it's way out and in front of all this stuff. So I kind of see what's going on. You know, by the way, what is this? This question 21 wants me to graph this. There's my graph. I'm sorry it sucks. But what they really wanted is, this is a matching problem, I think. Actually, I can match this with a picture from above. A, B, C, or D. Can you pick out which picture that might be? Well, maybe you don't have your book. That's the other problem. Well, I can. It's D. You can look at your book later. This looks a lot like D. So if it's multiple choice, it helps. So anyway, yeah. So maybe you will be asked to draw some crazy space curves, but dude, they are hard. They're hard. They're difficult. This one's not that difficult because I've trained you to think about the circular motion and to think about the helix idea. Let's do one that I might really ask you to sketch. I might really ask y'all to sketch this. Let's see here. How about, let's see. How about 4 cosine 2t, comma, 3t, comma, 4 sine 2t. So I would say, I would look at this and see the cosine and the sine, and radius 4, I would say, yeah, that's good old circular motion. But it's circular motion in the xz plane, and because that's the x and the z, and it's kind of, so the helix I did the other day had circular motion in the xy plane, and it was rising up around the z-axis. I think this one is got circular motion in the xz plane. Hang on, what am I saying? XZ plane, radius of 4 in the XZ plane, and it's going out and it's going around the y-axis. The y-axis is growing linearly as you have circular motion in the XZ plane. Are you guys okay?
Mm-hmm.
Is it because it's missing a trig function?
Well, it's because, yeah, the other day, this one was, I did a cosine t, sine t, and then a t. So I had the circular motion was in the xy plane, rising up linearly in the z direction. So circular motion in the xy plane, but as t moves, it's rising up. So it creates this helix. So this is circular motion in the xz plane, and then as t grows, it's heading out the y-axis here. Right. Now you know what? Maybe I write a question that says sketch this. Now watch this. Now hang on. for, maybe I just want it sketched for t equals 0 to 2 pi. Well, again, if you really got to pay attention to these directions like this, then I don't want you to sketch too little, and I don't want you to sketch too much. I want you to sketch this much of the helix. And then that's where your knowing about the period might come into play here. What is the period of this helix? It is circular motion, so it does have a period. What is the period of this helix?
Pi.
Good, it's 2 pi over that number 2. We already said it has a radius of 4, but it's 2 pi over 2 is the radius. 2 pi over 2 is the period, and you're right, that is pi. Now wait a minute, so if the period is pi, it's going to do 1 revolution in pi. So how many revolutions should I draw?
2.
I should draw 2 revolutions. It does 1 revolution in pi, and the instructions ask me to draw this much of it. That would be 2 revolutions. If I make the connection here, let me try to draw 2 revolutions of this thing. Okay, I'll try. I think it's going to go this way. It goes around behind this y-axis and then comes out, and look, I'm trying to hit this parallel spot right here. Here it is. That's it, completing 1 revolution. It's tricky drawing. Here it goes again. I'm going to do another revolution. And when I come back around, I'm hitting this spot again here. And now I just did 2 complete revolutions. And I got this radius of 4 labeled. I mean, it's okay. This ain't the best looking picture. It's not bad, actually. It's kind of tough to draw this stuff on a 2D blackboard. Hey, when it does end here, so I think I just plotted 0 to 2 pi. What's the y value here? I would like to know this y value here. Can you tell me? Well, I think I just did 2 revolutions. I think when I'm here, t was 0. When I'm here, I think t was 2 pi. So what's the y value? If t is 2 pi.
Oh, it's 6 pi.
It's 6 pi. Thank you. This is 6 pi. Again, maybe I don't have a real great one-to-one picture here. Let's just think about this a second. If that's 4, that's 18. Roughly, that's 18. So anyway, I'm not quite to scale here. That 18, that should be further on down. This is kind of, I guess these spirals of this helix are kind of elongated, quite elongated spirals. A lot of space in between them, I guess. I think that's because of this 3 times t. It's kind of growing in the y direction quite a bit. That's cool though. We did a basic helix the other day. Now I've adapted it a little. By the way, there's more to the helix. It keeps going forever, okay? It goes forever, and it goes forever back this way. Again, I kind of fall in this idea of saying this is where it starts, but t can be negative, and so it goes back this way forever. It goes this way forever. It's a forever helix. Just check this guy out for fun here. Here's another one. See, that's a helix with a little different action. But I would say circular motion in the XY plane. I could plug in a 0. That might be kind of interesting. If I plug in a 0, I get, what do I get? The cosine of 0 is 1, 0. Yeah, this one doesn't start at 1, 0, 0. Because when I plug in a 0, I get 1, 0, 1. So hang on, this guy starts at 1, 0, 1. So it kind of starts up here. And then I think it probably does its circular motion, but that z is rising exponentially. So guess what? I don't think the space between each spiral is linear. Like, I think these are kind of evenly spaced because of the linear growth in the y direction. I think I got exponential growth in the z direction here, and so I got a feeling that this helix is sort of, I mean, it's got these ever-growing gaps, this exponentially growing gaps between, I mean, it's just, right, I didn't mean that, I should have. These ever-growing gaps, I mean, it's just crazy. And then, if you want to plot points below 0, you kind of get this tightly spiraling thing down here. And the truth is, an exponential function, e to the t, is never going to be negative. So z is never negative on this. So it's tightly spiraling down here, but it never goes below here. It doesn't go below here. So it's just, this is kind of crazy. It's a helix with millions of tight spirals between here and here, and then millions more tight, well, but less tight spirals above that. Oh, geez. The point is to try to teach you to critically analyze these guys. I mean, it's our circular motion, but then the behavior in the z direction is exponential rather than linear. So, and that makes it a little different. And we're in 3D here with these helixes. We can't use our graphic calculators to help us with these, really. Yeah, so your graphic calculator helps you some. So most of this 12.1 is sketching. Hey, this is kind of cool. Look at this. I found this problem. 48. Problem 48 says y equals 4 minus x squared. This is in 12.1. They say, hey, represent this with a vector valued function, please. Represent this with a vector valued function. Well, first of all, maybe I'd realize that this is a two-dimensional curve, so I just need a two-dimensional curve, vector valued function. But a lot of students freeze up right here. They have no clue what to do, and it's so easy. I mean, see, what you got to do is you got to write this stuff in terms of t. I mean, what you have is a rectangular equation, which is a relationship between y and x. Okay, now, so you have to introduce a parameter t that's sort of where x has a relationship with t and y has a relationship with t. You know, that's what you need. You need x to be a relationship with t and y to be a function of t. And somehow, but they maintain this relationship here also. Watch how easy it is. You simply let x be t. By the way, that's one way. There's more than one way, actually. There's a lot of answers to this. But the easiest thing is, if you're trying to parameterize something, make parametric equations out of this, you let x be t. If you let x be t, you sort of plug it in there. Can you tell me what y is?
4 minus t squared.
Thank you very much. You just parameterize the curve. Are you with me? Good job. But there are other ways to parameterize it. I mean, here's another one. somebody might decide, I want x to be the square root of t. And if x is the square root of t, then this is, then I plug it in there and I square it, then I get t, so then what's y? 4 minus t. You follow me? Now, when you do these, here's another one. I could let x be, maybe I want to do this kind of parameterization. Watch. I want to let x be cosine t. If x is cosine t, what's y? 4 minus cosine squared t. Do you agree?
Yeah.
Listen, I'm going to go ahead and show you something. So the question was, can you come up with a vector value function? Can you please parameterize this curve? And we did. And this is the easiest and smartest and best way to do it. But I got a little creative, and I got some other answers. There are more than one answer. The truth is, parametric equations are, all these, if you kind of solve for t and try to eliminate the parameter, you get this equation. The relationship between y and x on all these is this relationship. But due to this parameterization, there's a lot of different things going on here. Do you know what this looks like? Do you know what this is? Can you tell me what this is?
Upside down parabola.
Upside down parabola, one little other phrase, pushed up 4.
Yeah.
Upside down parabola, pushed up 4, here it is. He's exactly right. Now if I drew him, I would put little arrows on the ends. Hang on, I don't want to put little arrows on the ends. Why not? Because I want to, if I'm drawing this guy, I want to show the, so as t increases, as t increases, t is like x. So as x increases, t increases. I believe I'm moving left to right. I believe this is the direction of motion for this parameterization. Now, a few minutes ago I said that we have these 3 answers. We have multiple types of answers we could do, but I want to point out what happens. When you parameterize like this, you've really just restricted yourself quite a bit. Can you tell me about some restrictions that just occurred here? In other words, this graph is different. I'm sorry, this graph is different. It's a parameterization of this curve, but the restrictions due to the type of parameterization you chose, you've restricted some things here. Because you decided to use a square root, I know it wasn't you, it was me. Because I decided to use a square root, I got some issues. I can't have negative t's. And I can't input any negative t values. So I have to start with 0, and then I have to plot positive t values. Well, you know what? That's going to result in, actually, just this half of this parabola. So this vector valued function is this picture. This vector valued function is this picture. So due to the nature of how you parameterize things, you put restrictions on the graph. This one's beautiful. Check this out. This one's cool. I got major restrictions on this one. Check this out. Hang on. My first thought is, oh, dude, man, it's just that parabola. It's just that parabola. Well, wait a minute. Now, cosine t. Now, you're allowed to plug anything you want in for t. But you know about the output for a cosine function? You tell me. You can plug in anything you want for t, but what does cosine spit out? You guys know that it's a, you plug in any angles, but the cosine of any angle is always some fraction between -1 and 1. Cosine lives between -1. So no matter, I can plug any kind of t I want in there, but it's only going to spit out values between -1 and 1. So that just told me that the x coordinate of this vector valued function is restricted to living between -1 and 1. So it's not this entire parabola, but it's this much of the parabola. It's not that part, and it's not this part. It's where x lives between -1 and 1. Because cosine lives between -1 and 1, x has to live between -1 and 1. And there's this is it's the same damn parabola, but it's got this restriction due to the nature of the parametrization we chose. I've got these restrictions on here, and I really have this. And then you may want to investigate that does it move left to right or right to left? The truth is, as we let t go, it's going to go from, if we start at 0, the cosine of 0 is 1.
Yeah.
So that would be here, t equals 0. Okay, so then as you plotted more points, it's probably going to move this way. You know what? When it gets to pi, check this out. When it gets to pi, what's the cosine of pi? Cosine of pi? -1. Thank you. So when it gets to pi, you're here. Okay, now what happens after pi? You're pi over, past pi. 7 pi over 6, 4 pi over 3, 3 pi over 2, past pi. Then you get to 2 pi. When you get to 2 pi, the cosine of 2 pi is back to 1. So you know what this guy's doing? He traveled over here, he hit this, and now he's traveling backwards. And he gets back here, it's t equals 2 pi. And then you know what he does after that? He goes back, and then he goes back, and then he goes back, and then he goes back. This is beautiful. This guy oscillates back and forth on this path. He's on this parabola, oscillating back and forth on this little piece of the parabola. I mean, what a cool set of parametric equations. I mean, it seems like that would be useful. I could program something to do that, go back and forth all the time. Maybe it would wash my car or something, I don't know. All right. The question, I went way overboard with this question. The question was, can you please come up with a vector valued function for this? And the point is, there's many acceptable answers, but they all have different graphical representations. I think the most logical answer to go for would have been this one, though, which kind of does represent the curve without too many restrictions or any restrictions. Right. All right. In 12.1, I didn't get to these questions. There's these questions. There's 53 through 62. These are kind of tough, but I like them. And I probably would like to put a test question on here. Let me just try to grab one of these. Okay. I'll try this 58. So 58 gives me this. What they give me is 2 surfaces. You're given 2 surfaces. Now surfaces, that takes me back to chapter 11 when I learned about surfaces. So the first one they give me is x squared plus y squared plus z squared equals 10. Is that right? Did I read that right? Number 58. Yes. And then the next surface they give me is x plus y equals 4. So these are my 2 surfaces. Now, maybe I can say this, or maybe I should write this. When 2 surfaces intersect, I'm going to write this little phrase down here. When 2 surfaces intersect, they form a curve of intersection. They form a curve of intersection. And how do we represent curves in space? We represent curves with an R of t, a vector value function. So these surfaces are given, in x, y, z notation, surface notation, but the curve where they intersect is a curve. It's not a surface. Where they intersect is a curve. And we can represent this with a vector value function, and that's the question. Please come up with the curve of intersection for these two surfaces. Wait till you see how easy this is. You ready? This is so easy. It sounds complicated. It seems weird. It's so easy. Actually, the book even made it easier. The book suggested to you how to parameterize it. I don't like to do that. I like to just give you this question and show you how easy it is to parameterize something. Kind of like I just did, you guys, in the last problem. Maybe I should just let x be t. Okay, now watch what happens. If I do just let x be t, then I'll go in here and I'll plug in a t. If I plug in a t here, and notice, see what's nice is that I think in all these problems, you have a 3-variable surface and then you have a 2-variable surface. So you can plug a t into this one and then you can find y. What would y be?
4 minus t.
4 minus t. So I'm 2/3 of the way done here. So now I have x and I have y. How do I get z? Well, then I maybe go up to that first equation and plug in my x and plug in my y, and I'll get z in terms of t. That one's kind of a mess, but let's do it. X is t, so that's t squared. Y is 4 minus t, and it's squared. And then that's a z squared, and it adds up to 10. And I want to solve for z. It does get a little nasty here. But it is, what is? Z squared would be 10 minus t squared minus 4 minus t squared. Oops, 4 minus t squared. I could FOIL that out. Maybe that would help me a little, but it might help me a little. I kind of don't want to. If I want to solve for z, guess what I do now? Take the square root. And technically it's plus and minus the square root of 10 minus t squared minus 4 minus t squared. And that's what I put for my z. I mean, was that easy? That was easy. If I had some cool technology to do some cool 3D graphing, I could type this in and see this curve of intersection. Hey, just for fun, I think this does simplify quite a bit if I'm thinking right here. Oh, no, it doesn't. Not as much as I thought. Yeah, I was thinking maybe the t squareds would go away. No, they won't actually. He's a negative t squared. This will be a positive t squared, but then it'll be negative, so they won't really go away. I'll have negative 2t squared. I'll have some other terms. Anyway, it won't really clean up that much. I'll just leave it like that. So I think that's kind of easy. If I do read the book for this problem, they had a different suggestion. They suggested to let x equal 2 plus sine t. So their suggestion for parameterizing the curve, if I go with what the book said, they said let x equal 2 plus sine t. Now guess what? If I'm just thinking out here in the world like I do, I wouldn't have come up with that. I wouldn't have come up with that. So I did what I came up with. Because this always works. Let x be t. Get y, and then you plug in, you get z. But this is not the most efficient parametric equation perhaps, because of the plus and minus and the square root, things don't plot out that well with this kind of stuff. Let's just try it with their suggestion. If I do let x be 2 plus sine t, then I'm going to plug it in this equation, and 2 plus sine t plus y has to equal 4. Right, you guys? I'm plugging it in here for x, and then I'll solve for y. So I'll move the 2 over, and I'll move the sine over, so y will equal 2 minus sine t. Is that what I just came up with? Because I moved the sine over. I subtract 2. Yeah. So there's my x. They gave me that. I came up with that. And now I'll plug that x and that y in here and try to get z. So x squared plus y squared plus z squared equals 10. And I bet you this cleans up. I think that was their point. So I'm going to FOIL this out. It's going to be 4 plus 4 sine t plus sine squared t. Maybe it doesn't clean up as much as I thought. I'm going to FOIL this out. It's a 4 minus 4 sine t, when you FOIL this out, plus a sine squared t, plus a z squared equals 10. I am trying to solve for z, so I'm going to move everything to this other side, but hang on a second. The 4 sine t cancels. Those other 4's don't cancel. That's an 8. When you move it to the other side, that's my z. When I move it to the other side, I got an 8. I move it over here, subtract it from 10, that's a 2. And what I have here is 2 sine squared. When I move it to the other side, it's a negative 2 sine squared. Are you guys okay?
Yeah.
You following my math? All right, now I see something, because I know I work with sines and cosines a lot. I know about these identities. If I factor out a 2, I have 1 minus sine squared. And 1 minus sine squared is very famous. 1 minus sine squared is?
Cosine squared.
Cosine squared. I'm going to move up here where I got a little room. So now I got z squared equals 2 cosine squared. I'm going to take the square root of both sides. This time I don't need a plus and minus because I got this cosine function. I don't think I need plus and minus. I do get the square root of 2, but I get the square root of cos squared. The square root of cos squared is cos t. So, another parameterization would be, according to their directions, let x equal 2 plus sine t. We discovered that y is 2 minus sine t, and now we just discovered that z is the square root of 2 cos t. And maybe this is a smoother, plotting, better parametric equation for this curve.
How would they go about kind of making the assumption that x is 2 plus?
How did they? That's a decent question. I'm not sure, but I'm going to guess, and I'm hitting just a teeny bit of overtime. Bear with me. So what I tried to teach you is that given these two surfaces, is it hard to find the curve of intersection? Is it hard to actually find it, like write the equation? And the answer is no. You can start by letting x equal t and play the game, or take their suggestion and play the game. Okay, so here is the hard part of this: sketching. They wanted me to sketch all this. Well, I didn't pick a very hard one to sketch, actually. Do you know what that is? You're supposed to know what that is.
It's a sphere.
Thank you. It's a sphere. It's centered at the origin, and its radius is?
Square root of 5. Square root of 10.
Square root of 10. Okay, good. Square root of 10, which is about 3. So let me, watch this. I'm going to try to, this will be a little mini picture here. But it's a sphere centered at the origin, roughly radius 3, square root of 10. Here it is. It's a sphere. Okay, it's a sphere. Do you know what this is?
I think that's a linear line.
Okay, it makes you think of a line in the XY plane. It makes you think it's a line in the XY plane, but in our 3D world, which we jumped into a few weeks ago,
plane.
It's a plane. You know, in 2D world, for just a second, if I plot points, it hits, plug in a 0 for x, it hits y at 4. Plug in a 0 for y, it hits x at 4. So it is this line, but wait a minute, it's not a line in our 3D world. It's a plane.
Parallel to
The z-axis is coming out at you. Z is missing here, so it's parallel to the z-axis. So it's standing up straight, coming out at you. It's parallel to this z-axis that's coming out at you. Now can I transfer that to this picture? This is the z-axis. It hits the x at 4. Ooh, keep in mind that's 3, right? It hits the x at 4, it hits the y at 4. It's a plane. And it rises up like a plane here. It does not bend toward the z-axis. It doesn't. That's parallel. So now, it's a plane slicing through a sphere. Can you see the curve of intersection or describe it to me? I see it. There's a sphere sitting here, and this plane is cutting it right here. So what's the curve of intersection? I think there's this sphere right here, and it's bulging out a little bit, and this plane cuts it right here. I'm off camera. There's this sphere coming out. This plane is cutting it. The curve of intersection is not the little bulge that's sticking out, or it's just where they intersect, which I think is a circle. And I'm going to try to draw it. But it's funny, it's out here, it's centered out here somewhere. I guess it's centered. Well, no, it's not centered on the sphere. It's centered interior to the sphere, I guess. It's got some kind of a little radius. It's some kind of a little diagonal circle sitting there. Or maybe, would it be an ellipse? Wait a minute, this is a sphere. If you cut a sphere with a plane, I think you get a circle, no matter what. If it's a sphere, and you cut it with a plane, I think you get a circle. So there's a little circle sitting here. And guess what its parametric equation is? Guess what its parametric equation is? That, or that. The hard part wasn't coming up with this equation. The hard part was sketching it. And that one was kind of a rather easy one in a way. A plane and a sphere intersecting. The curve of intersection is what these are two surfaces, but we're after the curve of intersection. So I would like you should maybe try more of those guys. Some of them are easy, some of them are tougher, some of them are easier. Again, actually, getting the equation isn't too tough. But maybe I'll quit today. I didn't get too far. Maybe Friday I'll dive into 12.2 a little bit. I would like to get into 12.3. There's more to say about 12.3. Like I said, we can do some actual good physics problems about launching projectiles. There's a bunch of those in 12.3. So we'll quit today. Thank you for listening and being here.